Hi everyone, this is 2.8, derivative as a function. And first we want to recall what derivative means. And recall that the slope of the tangent line of f of x at x equals a is this. This is how you calculate the slope of the tangent line at a particular point. This is known as the derivative of f evaluated at x equals a. The derivative as a function of x is then this. So notice the real difference is I'm replacing all a's with x's. And the purpose of this is that a isn't a variable, a is an actual value of x. So just to give an idea, here's kind of the visualization. If we have a function of x, let's say this is the graph of the function, x can be any value, x is variable. But once we assign a value for x, let's say we assign x equals a, then what you do is you project to the function to get what is called the point of tangency. So this point is the point of tangency. And you create a tangent line at this point. So let me do that in blue. That is the tangent line. Now the slope of the tangent line at the point x equals a is this. But what we're trying to do here now is generalize that and say, well, what if it's not a fixed value? What if it just moves around? So it's kind of hard to imagine, but if you imagine this point moving, the slope is going to change. In fact, the line is going to be different as well. So what this does is this creates a function for that slope. So plugging in any x value will give you the slope at that given tangent line. All right, so now onward to the next example. I asked to find the slope of the tangent line of the function f of x equals x squared minus 2 for these given x values. So x equals 0, x equals 1, x equals negative 2. Now normally from previous sections what we've been told to do is to find f prime of a particular value. We would just plug it in. So f prime of 0 would be the limit as h goes to 0 of f of 0 plus h minus f of 0 all over h. But, well, then what? So then when we have this, we would simplify, find the limit, then we'd have the value for x equals 0. Then we do the same thing for 1, then for negative 2. But what I just explained from the previous screen, instead of doing it for 0, or 1 and negative 2, let's just do it for x. So f prime of x instead of 0. And then once we have this will be an equation for the derivative. Then we can just plug in 0, 1, and negative 2 after the fact. So it's a little quicker. So this is the idea behind derivative as a function, opposed to derivative as a particular value. Okay, so let's see. So we're going to find this derivative. So there's a limit as h goes to 0 of, it's all over h. The first part I'm going to write these in brackets because otherwise you may forget to distribute and so on. So the first part in brackets is f of x plus h. So it's f of x is x squared minus 2. F of x plus h is x plus h squared. You see that? Minus 2. Minus f of x is just the original x squared minus 2. Perfect. Okay, the negative distributes. So we get negative x squared plus 2. X squared, well, I guess x plus h all squared, what's that? So let's do that over here. X plus h quantity squared, if you don't remember, is x squared plus 2xh plus h squared. And that's by just foiling this out. Remember, it's the first one squared, 2 times their product for the middle term, and the last one squared. Okay? So in front of this negative x squared and positive 2, we're going to have that negative 2 here, and then this is going to be x squared plus 2xh, and then plus h squared, squeezing that in, all over h. Limit as h goes to 0. And here's what happens, and here's what will always happen. Everything except for anything involving h will cancel out. X squares cancel, 2's cancel. Notice everything that survives on top involves h only. So what we have left now is, let me write it over here, limit as h goes to 0 of, on top, 2xh plus h squared all over h. On the top, they both have h in common, so if we factor it out, we'll have h outside of 2x plus h all over h. Now we can cancel out the h's. And what we're left with now is just 2x plus h. And what happens in the limit, as h goes to 0, all we're left with now is just 2x, just 2x. So in the limit, the answer is just 2x. So now this is not the actual answer of the question because we still need to take care of plugging in these. And obviously I used a lot of space here, but it was good because otherwise we would have used the same amount of space for a particular number. Instead we've kind of handled all three of them in one fell swoop. Because now we know to just plug in x equals 0, 1, and negative 2. So let me clear this up and show that right now. Okay, great. So what we just found was that f prime of x is 2x. So that means for problem 1, problem 2, and problem 3, these parts of this exercise, we're just going to plug in 0, 1, and negative 2 for x. Because that's what we're asked to do. So this is just 2 times 0, this is 2 times 1, this is 2 times negative 2. I'm just plugging them into x in this expression 2 times x. So we get 0 for the first one, 2 for the second one, and negative 4 for the last one. And I don't have too much space, but I think we have enough space to show it. I'm going to graph this just to give you an idea as far as what we're doing. So the function, the original function f of x equals x squared minus 2 is just a parabola shifted down 2 units. So I'm going to try to make it kind of accurate. I guess that's accurate enough. So if you plug in 1, you get 1 squared minus 2 is negative 1, so you'll get this. If you plug in 2, you get 2 squared minus 2 is 4 minus 2, that's just 2. Okay, so this is what the parabola looks like. This is f. Alright? Now what? Well, now we're looking at particular x values and we want to find the slope of the tangent line at those values. So at x equals 0, this is our point of tangency. At x equals 1, this is our point of tangency. And at x equals negative 2, this is our point of tangency. So now to actually find the tangent line, we're going to create tangent lines at those points, and then we're going to find the slopes of those. Well, we already did that part, but this is kind of showing that. So the tangent line here will be this one. The tangent line here will be this. And the tangent line here is like that. So I have these 4 lines, and here's what we've kind of just shown, algebraically basically, that the slope of this horizontal line is 0. Of course, horizontal lines have slope 0, so that makes sense. This slope has, or this tangent line has slope 2, which makes sense. It looks like it goes up 2 and over 1. And this one is definitely negative because it goes down and over opposed to up and over. And according to what we just did, it's m equals negative 4. Which makes sense because it is pretty steep. So, well, at least steeper than that one. So there we go. And yeah, so this is a nice visualization of what these numbers actually mean. Again, they're the slope of the tangent line at those particular x value points of tangency. Okay, so now I want to talk about different notation. So the notation we just saw was f prime of x. That's a prime notation. Of course, usually we say that y is equal to f of x. So f of x represents the y value of a point, or x is the x value of that point. Okay, good. But with that being said, then f prime of x is equivalent to saying y prime. Another notation due to Leibniz, who is a German mathematician, is dy over dx. And in fact, very often what we'll do is we'll take advantage of this notation a little bit and pretend that this is multiplication, and we essentially rewrite it as d over dx times y. I said multiplication, but we're kind of more treating it as a function. So d over dx is known as the differential operator. So let me see if I have space to write that here. So the d over dx part is called the differential operator. Okay? And with that being said, to find the derivative, you can say a few ways. You can say derive as act of finding derivative. You can also say differentiate. So to differentiate is to find the derivative of a function. So we say if f prime of x exists, then we say that f of x is differentiable. Now, it's possible for a function to have no derivatives anywhere. It's also possible for a function to only not have derivatives in some locations. And it's a little hard to fathom what that means, but basically the limit wouldn't exist. And here's an example of this. So consider f of x equals radical x. Let's find its derivative. So we want to find f prime of x. And that's, of course, the limit as h goes to 0 of radical x plus h minus radical x all over h. Simple enough. What I'm going to do here is I'm going to multiply top and bottom by the conjugate of the numerator. Now, if you don't remember, conjugate is just a middle sign change of an expression involving radicals. So it's going to be radical x plus h plus radical x. Let me see if we can squeeze it in here. Radical x plus h plus radical x. Okay, why are we doing that? Well, we're doing that so that we get rid of radicals on top, because the numerator will now be a difference of squares. So let's see. So we'll get limit as h goes to 0 of, on the bottom, it's h times the quantity x plus h in radical plus radical x. So the bottom, I'm not going to distribute that h. I'm going to leave it like that. That's fine. On the top, if you actually FOIL this out, you can if you want to, but I'm just going to recall for us that a plus b times a minus b is what is called the difference of squares. It's a squared minus b squared, and that's a very general thing that happens all the time. This is something that comes up a lot, so we need to know this. So here it's going to be radical x plus h squared, which is just x plus h, because when you square a radical, the radical cancels, minus radical x squared, which is just x. So notice what happens here is the x's cancel out, and I said that will always happen in the numerator. You want it so that your non-h's cancel, and here the non-h's are x, and the x's cancel. So now what we're left with is a limit as h goes to 0 of h over h times that. And of course, this is why I wanted to leave the bottom factored, so that these h's can cancel. If we FOILed it, or if we distributed h back in, we wouldn't actually see that cancellation as nicely as we do now. So now that we get that cancellation of h's, now what we're left with is limit as h goes to 0 of 1 over radical x plus h plus radical x. And now we can say as h goes to 0, what we're left with on the bottom is radical x plus radical x. So altogether this is 1 over 2 radical x. I'll box it up. That's the derivative of the function. Now, what does it have to do with not existing? Well, when does this not exist? It doesn't exist when x is 0. Even though 0 is in the domain of the original function of x, f of 0 is just 0, radical 0, 0, that's fine. F prime of 0 doesn't exist. So we could say here that f of x is not differentiable at x equals 0. Why? Because the derivative evaluated at 0 doesn't exist. Right, so next I want to go over this concept that I think is pretty fundamental, but it's kind of visual. And it's the idea that smoothness of a curve is equivalent to the existence of derivative at the point where it is either smooth or not smooth. So if it's smooth, then its derivative exists. If it's not smooth, then its derivative doesn't exist. And when I say not smooth, I mean sharp edges. So we'll see that with these two examples I've given you here. So the first one is f of x equals radical x. We saw the derivative doesn't exist at 0. Now, from a visual standpoint, well, this is the curve of radical x. This is f of x. And notice it's smooth everywhere except it has this one point, and like at this point it's kind of just an end point, it falls off. So at this point, can we create a tangent line? The answer is no. Because if you were to create a tangent line, it's not really defined on how you would do it. So here's an example of a possible tangent line. Here's another one. In fact, there are infinitely many different possibilities for your tangent line because there's no exact sweet spot for the tangent line to balance on, basically. That's one way of seeing it. It's a sharp edge, basically. Now, similarly here for absolute value of x, just to remind us, here's what the absolute value of x is. As a piecewise defined function, it is either x itself when x is 0 or bigger, or it is negative x when x is negative. I know that sounds funny, but think of it like this. If you want to find the absolute value of negative 2, it's just positive 2. So what this says is that the absolute value of negative 2, we would use this one because negative 2 is less than 0. So the answer would be negative 2, which is positive 2. So either you keep the number the same if it's positive, or you negate it, meaning you make it positive if it was negative, because double negative is positive. Okay, and this V shape here is the curve of f. And so a straight line is technically considered smooth. Its derivative exists. In fact, if you think about it, the tangent line for a straight line is just itself because it's already a straight line. It's kind of a silly example, but it's definitely true, certainly true. Now, y equals x is this positive slope line here, and y equals negative x is this one. Now notice we only have y equals x when x is positive and negative x when x is negative. So that's why we have this V shape. That's why I wanted to show this so we can see and believe me that this is the graph of absolute value of x. Just as an example, notice that the absolute value of 2 would be positive 2, and the absolute value of negative 2 would also be positive 2. So it's reflective about the y-axis. Great. But now, is there a sharp edge? Yes, there's a sharp edge. We can all see the sharp edge is at this vertex right here. And it makes sense because there's no point, or there's no spot where the tangent line can balance on. And I'm not going to show you, but I will say that if you were to find the derivative of this, well, its derivative would actually also be piecewise. In fact, before I show that, let me show this one just to remind us what happens here. Here, the derivative was 1 over 2 radical x, which doesn't exist at 0. So f prime of 0 doesn't exist. All right. And this is going to sound a little weird, but on to the next example. I won't find the derivative, but I will tell you something. I'll tell you what the derivatives are. I say are because there's two. Now, let's think of this geometrically. Derivative is what? It is a slope of the tangent line. So the line y equals x has slope 1. The line y equals negative x has slope negative 1. Okay? So the tangent line at any of those given points is just that line itself. Meaning, the slope of the tangent line for x is 1. The slope of the tangent line for negative x is negative 1. So this is when x is positive or 0, and this is where x is less than 0. So far so good? I think so. But now, what happens at 0? Well, f prime of 0 wants to be two things. Technically f prime of 0 would be 1. It wouldn't be negative 1. But the problem here is that the way derivative is defined as a limit. And since the limits from each side aren't the same, one's positive, one's a negative one, this limit doesn't exist. And let me just say because the limit from the left doesn't equal the limit from the right. It's kind of hard to say that, but let me just say limit from left doesn't equal limit from right. That's kind of a weird notation, but I don't want to write it too much. But let me just say limit from the negative side doesn't equal the limit from the positive side. And you can kind of see that because their derivatives are going to be different. And geometrically it comes to this whole balancing act. Is there a smoothness or is there a sharp edge? If there's a sharp edge, we can't define a sweet spot to balance on. So that's really what it is. And honestly, that concludes 2.8. That was basically it. 2.8 is pretty abstract in some sense. It's very conceptual. There's a lot of ideas and it's kind of theoretical. We did explore on how to find the derivative, but it's through what is called the definition of derivative. So what I gave you, f prime of x equals that quotient thing we saw. That, by the way, is called the difference quotient. We won't need to know the vocabulary of that, but let me just say that that is the definition of derivative, and we'll be using that to get to shortcuts. So beyond this, once we hit chapter 3, which is in the next video, we're just going to see shortcut on shortcut on shortcut, and it's going to be fantastic. I'll see you then.